Thank you. So I'm Pierre Halftermeyer. Really glad to be here today. Today we are going to talk about graph pattern matching and how to master it with quantified path pattern. So let's go directly. So I will tell you some story about graph pattern matching. So if we are here today, it's because we love Neo4j, we love graphs, we love Cypher or query language or beloved query language. And why do we love it? It's because it's a query language with ASCII art-based patterns and a language which is graph pattern matching centric. When I will say GPM is for graph pattern matching. So we like to draw our patterns with parentheses, with arrows, because it's cool. When you learn Cypher first day, it's like, wow, that's great to code like this. So we like that. And when we want to build a Cypher query, what we know is it's easy. It's ASCII art, patterns, drawing, and that's it. We have our query. But sincerely, it's not always the case. Sometimes it gets more complicated. Let's take some example with some use case. And this is a supply chain analysis use case called rank n supplier. So it's about parts of or product you are selling or you are buying. It's about suppliers, it's about buyers, it's about purchases, it's about dates. And the user story is you want to find suppliers of suppliers for a given product and from a given rank 0 site. So you are in a site and you want to know the suppliers you have and the suppliers of your suppliers. Let's say this is the picture. You want to have several alternatives for a given purchase, because if there is a shortage for one of your supplier, you want to be able to use another way to get your product. For instance, if you are building planes and you need some let's say pneumatics. You want to be sure your two suppliers are not using the same the same caoutchouc, the same gum provider. So sometimes alternatives and security are an illusion, like in the case. We are the co mainly because it's the meme. It doesn't mean nothing. It's a co, but we have two alternatives, but the shortage is at the end of both paths. An example: we are at rank 0, and we want to have a vision of our supply chain. So we are a company named company with a logo, a generic logo. We are interested about this part, and from the purchase we know of this part. For some purchases, we can infer some relations between suppliers and suppliers of suppliers. For instance, we know there is this purchase. So from rank 0 to the other site, we have a link. From another purchase, we get another link. And then from all the purchases we know exists, we can find some path from rank 0 to the full supply chain. And basically it looks like easy graph pattern matching and Cypher to write, because Neo4j is for graph pattern matching and Cypher is the go-to solution for that. So that's what says some confident Neo4j developer when they see this query. So let's find out if it's true. This is the query, by the way. So the query is like more than 10 liners, but not a huge query. This is the graph pattern matching part. So we have a site, let's name it site 0, with some IDs, rank 0 site ID. And from buyer of purchase of part, we can get a path, site 0, and taking links buyer or suppliers, we get all the chain which is the supply chain. And then we have to filter that because it does not give us everything. We want, for instance, a relationship to alternate between buyer and suppliers, which is not as easy to write in Cypher if we don't use some tricks. So this is I call it the Cypher salad, because it's hard to write, it's hard to read, it's hard to maintain, and there is some awkward parts. For instance, this one. You need to check if the rank of some relationship in the past is even or odd, and check if it's buyer or supplier. And we don't want to see that in a query. It's not natural to do so. So it's not the right way to write this query. But does it scale? Can we use it? If we put no path length upper bound to this query, we will never get a result. And it's only with 1K nodes and 3K relationships, because there is a lot of paths to check and to filter. And because we check afterwards, we are creating a lot of rows. Here, I let you read the number of rows, but it's a lot. It will be easier to give the logarithm of it. So it does not scale. Maybe we can put an upper bound limit. So to say it does not scale, I will use the banana referential. So maybe you know the meme. So if it's a small banana, like we see here, it does not scale. And let's try with an upper bound to the length of the pattern of the path with upper bound 8. So we are taking supplier at distance 8 as a maximum. We get some results. So in 14 seconds in our data set, we are getting a result. So it's not that bad. We get something. So Cypher is useful, but it's not a real-time result like you would like to have. The confident Neo4j developers say, I'm still confident this will be easy Cypher, but maybe using apoc.path. Okay, moving the goalposts here, but let's say let's try it with apoc. Apoc is always or really often useful, so it's a good reflex to have. Filtering with from the parity of the index of the relationship is not necessary anymore. So it's less awkward this time, and the Cypher salad at the end of the query is less, so it's better. We still have to put an upper bound on the path, but it still works with upper bound 10, and we have a similar query time, but with a longer path, so it's better. Banana is bigger. We have something better. 13 seconds. What would say the customer of it, or the product owner? The user wants real time. So the anonymous Neo4j developer says maybe Traversal framework in Java is the solution. We don't want to hear that. So there is there is a turning of event in this story from version 5.9 of the Neo4j. There is a new feature available called Quantified Path Patterns. Quantified Path Pattern extend the pattern matching capabilities of Cypher, and it's guided from the ISO norm GQL initiative. And this is good. So first time this anonymous graph developer saw that, he's a GDS fan, by the way, but this time he saw QPP, Quantified Path Pattern, and let's say if he felt in love with that. And I have to come out right now. Now I am this developer, so now I will speak in my name, because we can be. It's less awkward to show what we will be producing. What does Quantified path patterns are or are not. They are not a new GDS algorithm. They are not a vector-based GPM matching approach. They are not a Neo4j LLM connector. None of that. So this is not like the hype we have right now. It's like regex, but for graph pattern matching. People familiar with regex will see something they can understand. There is a repeating part between the parentheses with the plus, that means one or many times, and sometimes 3 to 5 repetition of this arrow, etc. So it's similar to regex. They are making GPM better. It's not only a nice to have. Most traversal Cypher queries should be QPP based from now on. This is my opinion. And they are easy to learn. We have a great documentation at Neo4j, and in particular, we have a great documentation for graph pattern matching and QPP. So please read it. It's a nice piece of read. So I highly recommend it. Example of it. Let's build a not so toy story and not so toy query. So this is a graph with colors. So colors are like labels, and colors of arrows are like types. And we want to graph pattern match this. So it's a green node connected to blue, red, blue, red, blue, red, blue node, and all red nodes are connected to the same brown node as the green node. So not easy to explain, but quite easy to see as a picture. We want to traverse the graph, but by sticking to the brown node and with alternated colors. And we also want some property of blue nodes to be increasing all the way. And how can we do that? With the good old GPM way to do that, it would be just writing this path, green and brown or black, repeating until you have a blue. And then, so really easy graph pattern matching. We are almost there. And then it's like a hell of Cypher code salad. So we don't want to write the query. It's really complicated then to check everything. So we won't do that. Although the graph pattern matching is easy, the query is awful to write. With GPM with QPP, how would we do that? So this is the graph pattern matching part. So we want first to get the brown, green, and the first blue part of the query. So this is how it looks, and this is where it is in our graph. So we have the green, blue part of our pattern, and it's connected to a brown node. And then we have the repeating part of the QPP. So it's blue, red, blue, with checking always that there is an existing link between the red node and the brown node. And at each step, we will check that. So we can expand our pattern one step to the right, because we can pattern match it in the graph, and another time. And at each time, we are checking the T property is increasing from the first blue node to the second blue node of the repeating part. And this is cool because as we have written this repeating part with blue, pink, blue, and named all the objects in it, B1, B2, for instance, we can use B1, B2. They have a name. We can access their property. So where B1.t less than B2.t can be written, and we can filter while expanding. And in the same way, we can filter by checking there is an existing B2 brown node relationship. And we are expanding again, and at the last time at the end to know we are at the last node of the pattern, we are checking there is no existing last node to pink to brown node. So this is the last blue because there is no existing link to another red linked to the bond. So it's easier to show that than to say. And at the end, after the graph pattern matching part, it's only returning what we have, and we have named everything. The first BL node, and so this is the first BL node. So we have it in gray, and then the B2 is a list of every node of the expansion that was B2 at some moment of the expansion. So we have everything. We have all our blue nodes, and that's what we want to return. So let's return those blue nodes, and we have our pattern. And to sum up, GPM does everything, and that's what we wanted. We want a graph pattern matching centric language, and we now have it with QPPs. So GPM centric Cypher. Cypher is GPM centric again with QPP. This is the way we can write the query. Really easy, and it's the same query for our supply chain example. So it was not such a toy example. It was exactly the same, but with colors. It was easier to show. Does this scale with the same data set? And with no upper bound on the length of the path, we get all results in 3 milliseconds because we do filtering before expanding. We are not expanding then filtering. We are pruning the graph all the way and at each step. So we are not traversing useless relationship, and it's really efficient. So the max is 107 rows. It's like the log of the other one, and 3 milliseconds. So does this scale? Yes. Yes. Big banana here. No, there is no room for the banana on the screen. Second example now about anti-money laundering with QPP. I will go fast. So QPP is fighting against mules that are doing money laundering. So let's say you have some person which has a lot of money, but from dubious origin. Let's say it's from some criminal activity. He can give it to a mule, which is someone, an accomplice, and the mule will take a part of the money, let's say less than 20%, and give it to another mule that will do the same, take up to 20% and give it to another mule, 20% another mule, and then back to the first person that become an angel with a lot of money, not as much as at the beginning, but he can use it to buy a boat or house or a mansion or anything. So this is money laundering, and we want Cypher want to catch that. So what we can say is from a transaction to another one, dates should be increasing, so it will help us to prune our graph. And we have the 20% rule as the max commission you get. How do we handle that with QPP? Before QPP, we were doing that with a let's say straightforward pattern matching and Cypher salad. It was quite awkward, not as awkward as the one before, but a little bit awkward with a data set with 100K's relationship. We have like 33 seconds to get a cycle up to 6 length. No, sorry, it's only with 1,000 relationship, not 100,000. So it's not a big graph, and it's slow to get cycles, and with a limit of 6. So the query works. This is fine, but maybe we can do better. What's slow? Same as before. graph pattern matching, a lot of rows, and then filtering. It's not efficient. We are traversing too much of the graph, of useless part of the graph. Let's do a refactor of our graph. We can have transactions as nodes. We don't need anymore to have a monopartite graph with one type only to do pattern matching efficiently. We can do it, so it's not a requirement anymore. So let's use a transaction and account node, and let's graph pattern matching that. So there is an account performing the first transaction, and then we have a repeating part from a transaction to the next one. We can filter on this with where. We filter on the dates, and we filter on the amount. The amount should be decreasing at most 20%. And then we can do post filtering if we want, for instance, to check check the cycle is not 8 shape. So actual graph pattern matching and almost no Cypher code after. And we don't need anymore to put a limit on the number of hops in our query. So let's do that. Let's do that with a 100 times bigger graph. And we have in 600 milliseconds we get our results. We can do that in directly. Let me show you. This is this query, and here 300 milliseconds we get the result, and that's cool. That's cool. And there is no limit on the number of hops. It's with a plus or star. That's cool, but let's say it's not impressive because there is no really big cycle. So I will add some Easter egg here. Let's add a new cycle in the graph. I've just done that by adding some data, and I will run the query again. And now, in almost the same time, 481 milliseconds, we get one more cycle, but it's a cycle with 200 nodes. So it's like 200 joins with a SQL database, or it's like with any database you would have in the complexity something to the power 200. And with Neo4j, you have not. It's still linear in terms of number of hops you want to do. So the time of the query is linear in terms of the length of the needle, not the length of the not the size of the haystack. That's why we can say it scales great. So this is true. We have this, and this is the key. We have the filter part before the repeating part. This is pruning. So Cypher is not only anchoring and expanding; it's anchoring, pruning, and expanding. That's the new paradigm with QPP. So this is what I've just showed you live, but it was if the demo weren't working, and it was working, so great. It scales. A stack and needle can be huge. This is some benchmark I did, so it's exactly what I've just showed you. No need to go into details. It was easy to see. This is the last slide and maybe the most important slide of the deck. What are the takeaways? QPPs lie at the core of Cypher graph pattern matching. It's not like a new feature that is when I need to do graph pattern matching. Maybe if it does not work, I will use QPP. There is no reason not using QPP at the first time. It's like a new way to do it. And when you get used to it, it's easier to use QPP than not to use it. So play with it and try QPP, and you will write better Cypher. QPPs make GPM more precise and expressive. You are naming everything. You can filter where you want, there is much less awkward post graph pattern matching cipher. So when you have a QPP based query, it's easier to write, to read, to maintain, and in many cases more efficient, because QPP bring higher traversal performance because you're pruning. You are not exploring your neighbor and all the neighbors of your neighbors and all of their neighbors, which is a power law complexity. You are pruning and going straight to the target. So if you need some resources, there are some blogs you can get in the Neo4j blog. There is the official documentation that is written like a blog article. It's great. You can read it from top to bottom. It's it will be a great moment. And that's kind of it. Thank you very much for your attention and for being here. And I'm done. Thank you.